IP Psych, these are your Module 19 notes on visual organization and interpretation. So this is going to focus more on the perceptual piece of vision. So our essential question is, how does our interpretation of the information we receive from the environment influence our behaviors and mental processes? Our learning target is I can describe general principles of organizing and integrating sensation to promote stable awareness of the external world. This means that I can describe the principles associated with Gestalt, depth perception, top down processing, and bottom up processing. So, first, we're going to look at visual organization. And kind of the underlying idea of these first few things we're going to talk about is something called Gestalt. So, Gestalt, this idea, think of it kind of like it was really a historical perspective, much like humanism or behaviorism. Okay. And it was started by a group of German psychologists, and it can be defined as an organized whole. So, what does that mean in terms of perception? Is this group of psychologists emphasized our tendency to perceive and interpret certain configurations, like of shapes or images, like what you're seeing here, at the level of the whole, rather than in terms of their component features. So, what does that mean? When you look at an image like this, a Gestalt psychologist would say, rather than seeing each little individual piece, like get my little pointer here, like seeing this one little shape here, or this one little shape here. Instead, we perceive this as being one whole piece that belongs together. Okay, so that's what it means by the whole. So again, rather than seeing each individual like little kind of semi-triangle or this little half moon like Pac-Man shape, or as one line here or here or here, we see this whole image as being one image together. So we'll talk about what does that mean in terms of other things that we look at. So with form perception, here's what that looks like. So one example of that is something called figure ground. So this is the organization of our visual field into objects or some sort of figure that stands out from its surrounding, and the surroundings are known as the ground. So if I look at this logo from the Pittsburgh Zoo, hopefully you can see the bottom there, okay? I have figures. What may stand out to you or what would be figure depends on your perception. For some people, the figure is the tree, okay, the image in black, and the ground becomes this white negative space here, which if you look closely has some animals. For others of you, the figure could be the animals. That's what you notice first. And then the rest of the image, what's in black, becomes the ground or the background. Okay. The other principles here, other Gestalt principles, have to deal with grouping. And the idea is, again, when things are close together, we perceive them as a whole rather than as individual parts. So the different types of grouping, I am going to have you scavenger hunt style as an activity in class on Thursday or Friday, is to look for real life examples of these around your home or outside your home. So the first one is proximity. If you take a look at these group of lines, rather than seeing them as 6 individual separate lines, we see them in pairs is one way they're grouped together, but then we also see this as one complete image of this group of lines. Okay. Next is continuity. So we perceive smooth continuous patterns rather than discontinuous ones. So you're likely to perceive this as like this being one continuous line here, and this being another continuous line here, rather than seeing it as like this little part of the line and this little part of a line and this little part of a line or this tiny part of a line. Okay, so we group them together because of continuity. We perceive these as smooth and continuous. Next is closure. If you take a look at this panda, it's from the World Wildlife Federation. It's part of their logo. Notice that the panda is not complete. This also is something that you saw with our visual illusion that you saw with the dog, where it wasn't a complete image, but your brain fills in the gaps. So even though this panda isn't completely finished, like there's open spaces, our brain just fills in that all of this goes together to form, this one panda bear. Next is similarity. So when items are similar, we see them together rather than individually. So you probably see this as a group of triangles, a group of circles, and a group of triangles because they're similar shapes. We group them together. And then finally at the bottom, we get my little thing to go away there, is connectedness. So what you'll see at the very bottom, I don't want to move my mouse because then it'll disappear, is notice you have like these two circles or dots with a line between them. With that line between them, we view those as being connected together. We don't see it as six, had to count, make sure I said it right, 6 separate circles and 3 separate lines. We see them as like 3 sets, almost looking like little barbells. So all of these refer back to those Gestalt principles. Next, we need to talk about depth perception. So what allows us to understand and see and perceive objects in 3 dimensions? Because the thing is, when the images first strike our retina, they actually strike our retina as being 2-dimensional. So we need some other cues in our world to help us understand depth. Okay. So based on research by Gibson and Walk, they did an experiment known as the visual cliff. We know that the ability to perceive depth starts fairly young. So to test this, they created this device. This is plexiglass here, so baby's not in any danger. Okay. And notice that the pattern continues. The pattern starts on the floor and then continues down underneath this plexiglass. Well, before infants develop depth perception, they will crawl across that plexiglass with no problem because they don't realize that they're high up. But starting from a fairly young age, if you ask them, set them on the solid floor and ask them to crawl across, they won't because they know that that's far down there. And can I really trust this stuff here, this clear stuff, to hold me up? So now the question is, great, we have depth perception. What in our world allows us to understand that? So depth perception can be divided into 2 types of cues. Think of these cues as things in our world that help us to perceive depth. Okay. So first are called binocular cues. And they're called that, if we break down the word, is the word bi, we know it means 2, ocular, using our eyes. So it depends on both of our eyes to try it. So the first one is retinal disparity. So the way retinal disparity works is within your brain is computing basically the difference between the images as they strike each of your eye's retinas. Okay. And by comparing those images from your 2 eyes, it computes distance. So we know the greater the difference between the 2 images, the closer the object is. And you can see that through, you can make your finger look like this finger sausage. If you hold it up in front of you, it'll look like you have a floating finger. It's because your brain is trying to figure out, because it's super close, it's trying to figure out the difference between those images striking your retina. The other easier way to tell is through convergence. So this is your brain computing the extent to which your eyes converge inward or look inward when looking at an object. The greater your eyes have to look in towards your nose, your brain knows the closer that object is. So if you were to take your own finger, kind of like what you see her doing here, and bring it to your nose, you'll see your eyes go in, trying to look at that finger, and that tells your brain it's closer. Okay. The rest of the cues are called monocular cues. And that means that these depth cues are available to either eye alone. So you don't need both eyes to be able to tell them. For my artists, what you'll see is this is what allows art to come alive, are playing on these ideas related to monocular cues with perception. So a little art lesson here. So if we look here, the first one is called linear perspective. And linear perspective is if you think of looking at this painting, Renaissance era painting, that it looks like you have these parallel lines that draw the eye back. Okay. And they appear to meet in the distance. And what that does is, including these parallel lines, is it makes these objects appear closer. And as the line goes away from you, the objects back here appear farther away. Okay, so linear perspective. Next is interposition. If one object partially blocks the view of another, as we see here with these three shapes, we perceive this object as being the closest, the circle being the next closest, and the square being farther away, because we think this one is blocking this one, which is blocking the last one. Next is playing on light and shadow. So if we get two identical objects, the dimmer one seems farther away than the brighter one. So even though I have two circles here, this smaller one, see how it's darker, it's more dimmer. So that gives the appearance that this one is farther away, which makes it look like there's a dip here, when in fact it's just a two-dimensional surface. But because it's darker, it appears farther away than this outside circle that's lighter. More monocular cues are relative height. Okay? When we're looking at something like the St. Louis Arch, fun fact, the arch is as wide as it is tall. Okay. Objects higher in our field of vision, so up at the top, feel farther away than objects at the bottom of our field of vision. So it appears taller than it is wide, but that's because of relative height. Next is relative size. Okay. If we assume that two objects are similar in size, most people perceive the one that casts the smaller retinal image as being farther away. So if I'm looking at these two people in these kayaks, the one that casts a smaller image on my retina, even though in real life, or these canoes, kayaks, whatever they are, I know in real life they're probably similar size. But because this one is striking a smaller image on my retina, it appears farther away than this one here. Next is relative motion. So as we move, objects that are actually stable may appear to move. If you gaze at a fixed point, like if you're on a train or a bus or in a car, and gaze at a fixed point, the objects beyond the point will appear to move with you, which is kind of cool. So if you look here, you fix here, the objects in front tend to move away from you, the objects behind tend to move with you. Okay, which brings us next to motion perception. So how do we perceive motion? So motion is perceived partially is based on the assumption that shrinking objects are retreating, meaning going away from us, and enlarging objects are approaching us or coming closer to us. But for us to perceive motion, we actually need to see an object in relation to another object. So if we had no other frame of reference to compare something to, we wouldn't realize that it was in motion. So an example of this is called stroboscopic motion or movement, excuse me. This is if you've ever made one of those little flip books like that animate, you know it's just a rapid series of slightly varying images, okay? The image, any one single image isn't moving. It's when you combine them together, it gives the appearance of movement. Okay. A great example of that is what you're looking at here with this GIF showing the phi phenomenon. So the phi phenomenon is this illusion of movement created when two or more adjacent lights blink off and on in quick succession. So this looks like we can chase this dot around, but instead what's really happening is this dot blinks, and then the next one blinks, and then the next one blinks, and the next one blinks, and so forth, which gives the appearance of motion when in fact there isn't any. It's just a light blinking off or on. Next, we're going to look at perceptual constancy. So perceptual constancy is referring to our tendency to perceive objects as unchanging, meaning those objects have either constant shape or size or brightness or color, even as the illumination or the light around them changes and the retinal images change. So, one example of that is color constancy. So, this is perceiving familiar objects as having a consistent color, even if changing illumination, meaning the light around it, alters the wavelengths that are reflected by that object. So if you were to look at these two images down here, all three of these circles are the same exact color. And we know that they're the same exact color, even though, notice here is darker compared to up here, or up here is lighter compared to down here. All three are the exact same color, even though the lighting around it appears to change how we might perceive that color. Next is brightness constancy. This is perceiving objects as having brightness even while their illumination varies. So what this depends on is relative luminance, meaning the amount of light an object reflects relative to its surroundings. So fun fact, if you were to look at these two squares, they're the same color, just doesn't appear to be. So to understand the next parts, we need to understand that comparisons govern our perceptions. So looking at two objects and comparing them help us decide what it is that we're perceiving. How are we interpreting these images that are coming in? So again, perceptual constancy. We know things have constant shape, size, etc. So this is looking at size constancy. So we perceive objects as having a constant size even while our distance from them varies. So if I look at all these different cars, I know that they all have the same size, even though right now they don't appear to be. Okay, even though these are closer and these are farther away, I still perceive that size as staying constant, staying the same. Here is demonstrating shape constancy. So if we perceive the form of familiar objects as constant, even while our retinas receive changing images of them. So as you think about a door opening and you're watching this door open, each of these images strike your retina slightly differently, but I still know and perceive the door as remaining the same size, even though it looks different. It strikes my retina differently as it starts to open. All right, the moon illusion. If you've ever seen a full moon like this, you're like, wow, the moon is huge. Okay, let's watch this video about why that happens.
Have you ever gone out on a clear night, looked to the horizon, only to notice a gigantic moon staring back at you? Surely this is the biggest you've ever seen it. Maybe it's just closer to the Earth today? But what if I told you that that moon is the exact same size as every other time you've ever seen it in the sky, and it was in fact playing a trick on your brain? It's called the moon illusion, though an explanation of this optical phenomenon is still debated. What we do know is that when the moon sits closer to the horizon, it seems bigger, but if we measure it in the sky, it's the same size. You can test this by holding your thumbnail at arm's length and comparing it to the size of the moon. Do this when the moon is near the horizon and high in the sky, and you'll notice it doesn't change size. So why does our brain process it so differently? The main theory suggests that when the moon is near the horizon, there are many visual reference points, trees, buildings, mountains, with which its size may be compared. But when the moon resides high in the sky, there's nothing around it to compare, and it seems smaller against the vastness of the night sky. It's similar to an effect known as the Ebbinghaus illusion. Which of these orange circles is larger? It turns out they're the exact same size, but the objects surrounding them have an effect on our brain. The small circles are comparable to the horizon moon with smaller objects in sight, while the large circles are comparable to the high moon surrounded by vast night sky. Furthermore, our brains are used to objects moving towards the horizon becoming smaller, like clouds. So when our brain sees the moon at the horizon appearing the same size in our retina, it compensates for perspective and assumes it must now be physically larger. Still not convinced? Try bending over and looking through your legs at the horizon moon. The effect is gone because upside-down trees and buildings don't register as familiar objects and your depth perception isn't confounded. Or, for the less flexible, take a photo of both moons. Your camera won't suffer any optical illusions and you can clearly see the moon is the same size. Got a burning question you want answered? Ask it in the comments or on
Isn't that so interesting how something like just looking at the objects around can have such an effect on what we perceive as the size? So I have one more illusion for you, I think. Okay, yes, this is the last slide. Dang it, go back. Okay, is the Ames room. The Ames room. So you're going to hear Dr. Ramachandran. It's one of my favorites. He's down in UC San Diego. Explain the Ames room illusion. So here you go.
In interpreting the visual image, the brain has to resolve ambiguities. And in doing so, it uses all sorts of assumptions, built-in assumptions about the world. And because it uses all these assumptions, which we can investigate in the laboratory and discover, you can also trick the visual system. And this is what you call a visual illusion. This is the Ames room. It's a grotesquely deformed trapezoidal room. But the astonishing thing is, if you look inside the room looks completely normal. And the walls look parallel and everything seems fine. The reason is that the brain has a built-in assumption that the walls of rooms are usually parallel. This is something we've grown up with all our lives. And this assumption is so strong that it completely overrides the fact that the people are actually changing sizes. Even though in the real world, obviously people don't change sizes like balloons, here you're willing to see that because the assumption of parallel walls is much stronger.
I think in the case of special effects, what's happened is that we've become increasingly sophisticated.
Okay. Isn't that so cool of just the way you arrange and the angles of the floor and the walls can make it appear like someone is huge and someone is tiny. Okay, so the Ames room. So I only have this one question for you today, and that's what should I clarify before you complete the activity tomorrow? Really think of tomorrow as your next time in class, so either Thursday or Friday. So if there's any concepts that you want me to talk about, here's your chance so that I can make sure I go over them with you, because a large part of class for this module will be spent doing an activity where you're going to look for actual examples of a lot of the things that I described. So after you're done writing, I hope you all have a great rest of your day, and I will see you soon.